Most of you probably already noticed that our next speaker didn't make it to Dresden. So I should pass regards from Thomas de Beer. For personal reason, he had to cancel his flight yesterday. I got this message while you were listening a talk. So luckily you didn't see how I fell down behind my notebook. And I was thinking about it, and then I Martin is here. Martin is great in presenting. We know each other for quite a while, as Uwe has shown yesterday. I was asking him, I said, a no is a no is a no, and he said, no, it's a yes. I have a slide deck ready. You saw that mini APEC in Macclesfield a couple of weeks ago. And last night when he said good night after dinner, he also told me I prepared a fully different, a fully new slide deck. Thank you for jumping in on this very, very short notice. Great to have you here, and I love the idea you had for the slide deck.
Yeah, it's probably easier than deal with the headset. I do need to apologize right up front. As Sebastian said, this time yesterday I was not presenting. The question came in, and the question was simply, do I have a slide deck I could present? Great. And then I sat and listened to the questions during the days yesterday. And it made me actually think that I'm a little worried that we're forgetting some of the fundamentals behind the measurements that we're doing. So if you'll excuse me, I'm going to peel right back to 20 plus years ago, but try to bring you right up to date and answer some of the questions as we're going along. So let's see if this works. The reason I'm doing this is to get everybody to understand that we learn as we progress. And it's very important that we do not forget the lessons that we've learned. So yesterday, by happenstance, it flashed up on my Facebook page 5 years ago. I was going through Dresden station on the way to get a train to Berlin after this exact meeting. 5 years ago, I was getting the train. I'm doing the same journey today, but I'm getting the Flixbus. I've learned from the experience of getting the train. There's nothing wrong with the train. It runs once every 2 hours. So if you want to spend lots of time sitting at the train station, it's a good way forward. Second lesson. Well, actually, exactly this situation happened at the last meeting, and Thomas didn't come, and I stepped in. So one of the lessons that I should have learned is that to be prepared, just in case Thomas doesn't step in. So apologies, but I'm not going to ignore the concept of Thomas's presentation. I still include one of his slides that he's presented externally, and I've incorporated it into what I'll broadly call my my presentation. I said I'd peel you right back. This slide is absolutely fundamental to anything that we do. By that, there are reasons why we do PAT. There's some reasons that sit within the development space. You're trying to actually define which steps are critical. You're trying to actually identify which attributes are going to impact product performance. You're going to generate the process model that relates intermediate attributes to final product attributes. You're going to generate the control models, what you change in parameters to get those changes in intermediate attributes. You actually do all that development in a development mindset. You might not do it in development, but it's a development mindset. It's away from the process. You're not making process decisions. The complementary side of that is what you use it for in commercial manufacturing. There's nothing complicated here. You're actually running process and control models, and you need to actually implement and maintain those models. But I do want people to understand that there's already a concept, which is that you have data that's used specifically for monitoring and control, and there's a risk impact applied to that. If you're using a method simply to trend a process, not making control decisions, it's low risk impact. If you have a method that is actually used to make control decisions and particularly release a product, it's a high risk impact. You have to understand that risk impact. And because of that, it's not uncommon. I can't say it always applies, but many successful implementations rely on data that monitors during, that you use for control, but you have a confirmation of that by actually having a secondary analysis that's carried out typically offline, sometimes automated offline. But really think about that. Your high validation burden is on the at-line method, where you've taken a sample. It's much easier to validate, not only build, but validate that method as an offline. So this concept of continuous stream of data used for monitoring control, occasionally checked by confirmation, is a key concept. And in fact, on a new product submission, they expect you to actually identify the frequency at which you do measurement to the process dynamics, how fast the process is changing, and have an increased amount of data when the process is in a transition state compared to when a process is in a stable state. I don't want to get ahead of myself, though. Application specifications is much, much more than which technique. And I'm intentionally going to use examples later on that blurs the line between different techniques, but get people to understand that it's the source of the data that's the critical thing. We've fundamentally got to make sure that whatever we choose to use has the specificity and selectivity that we need, has the sensitivity that we need. You've seen from Steve and Phil yesterday, it's got to have the scrutiny of scale and the frequency that we need. There's no good actually averaging a big block of data to try and indicate an attribute that's changing on a very small frequency basis. You've got to actually make sure the application is capable of all of these. Now, near-infrared is fundamentally a useful technique, but there's a difference between it being a useful technique and why it's a useful technique, and choosing near-infrared. So let's examine this just a little bit. Near-infrared is a very powerful technique, fundamentally because the functional groups that are found in our products actually have combination and overtone absorptions in the NIR region. We get a response in the region. I'm going to try to make everybody think about that a little bit, though, as we go further on. It requires little sample prep. Shine light at a sample, you measure either light going through a sample or that gets diffused or reflected back from a sample. It's fast and it's non-destructive. And it's very amenable to move online. So there's lots of big positives here. But don't ignore the fact there's a couple of major drawbacks. We've got sensitivity limitations around near-infrared. Near-infrared has improved significantly in the last 20 years. Our ability to actually collect data from near-infrared has improved significantly. We still have a lower ceiling where if the concentration goes low enough, we cannot measure. It's not an infinitely extendable methodology. You simply get to the point that the peaks that you're trying to look at are no bigger than the noise in which you're looking. You've got to understand that. We also have a challenge as an industry. Near-infrared is so well established, there are numerous different fundamental technologies that are deployed. And we have to understand the differences as well as the similarities between those. It's not simply around technical transfer, it's actually understanding what it's telling us. Okay, so let's actually look at some real examples. I said I'm going to peel back to examples that have been given. So let's look at pharmaceutical blending. We put materials in a big steel drum, we rotate those materials, but they're loaded in a way that it's actually stratified. We don't throw everything in together, so we put them in components. Typically, the API component is one of the components that's added in the center. So I'm asking people to visualize now. What do you think happens when that rotates? The first signal that you see is the excipient at the top, and gradually over time, you start to see the other components appear in that outer layer. So really what you're doing is actually comparing, whenever you look at our trend lines, it's how fast they reach an equilibrium point of what was individual components at the beginning have reached a uniform mixture at the end. Because it's that uniform mixture that we press into tablets or put into capsules. Okay, I said I was going to take everybody back to 20 years ago. From my memory, this was 2002. Steve or Phil might remember differently. It's of that era. I've purposely put about 2002. The reason I know it was about 2002, people have got to understand, this is as home-built as you can get. It's a commercially available spectrometer and measuring head being powered, I don't know whether I can use the pointer, being powered by a battery that's in a second box that we've got bolted to the frame of the blender. In that box is actually the gravity switches. At that point, there was no fancy accelerometer. 2 gravity switches, switch, not switch, switch, not switch, that was actually starting the spectrometer. If you look carefully, duct taped to the top of the spectrometer is a laptop. It was started before the run, and it sits there and waits until there is a trigger to collect data. This does not look like a GMP system, does it? This is a GMP batch of Istin, a commercial batch of a product that made it to patient. There was a risk impact assessment made of the introduction of the Sapphire window, which clearly showed it did not impact the process. We're not using the data to make any control decision. We're learning when the process is finished. We were allowed to do that. Not only were we allowed to do that, this data was actually shared by Steve at the first FDA Science Board meeting that kicked off the whole PAT initiative in, when was that, September 2002, something like that? Yeah. Real data on a commercial blend, because we understood we were not making a control decision and we weren't messing up the quality of the blend. What we were doing had no impact. We were learning what we didn't know. And there was a question yesterday about, you know, people run granulation and there's an assumption that they know what the end point of granulation is. I guarantee you, when you put a PAT system on any of our process steps, it's that time when you find out how variable the population is, whether you've really reached the end point. The most common way to do development is a development activity on a commercial system, as long as you don't mess that commercial system up. I've seen examples where they didn't do the risk assessment and have messed the commercial system up. It's not, don't take it as read, but if you do the work, you can do that.
It's over 20 years ago, so I can reveal this. That exercise did change the process because we had to wait for the president of Pfizer manufacturing to come along to demo it. And we found that if we did the curve immediately the blender was loaded, we got one pattern. If we waited for the president of manufacturing 3 hours later, we changed the curve.
And just to build on that, we also understood why. When the bin was being left stationary, waiting for the 3 hours for the president of manufacturing to arrive, the vibrations in the factory actually created a deeper stratification. The end of the profile looked the same. The start of the profile, the shape of the profile was totally different. In fact, we caused a total panic in the plant because we weren't doing the demo. The head of the plant was actually, took the head of manufacturing up to the computer and said, look, I press this and you'll see the curve do that. And he pressed it and the curve was totally different shape. And it was like, geez, what have you done to our system? Like, we haven't done nothing. That is what is happening that you do not normally see. Okay, I'm getting a little behind, but I do want people to understand that this fundamental instrument was literally just a lab piece of equipment. Yes, there was a selection involved. We made sure that it used an in-gas detector. Now, I'm going to use this chart several times, so I really want people to understand it. When you're looking at NIR spectroscopy data, you have a collection of absorptions that are combinations. You have a collection of absorptions that are first overtone. You have a collection that are second and third overtone. So even now, if I overlay the box that's an in-gas detector, guess what? I'm seeing, oh, getting carried away here. Go back. Must be the other way. You see a collection of spectra that are actually the first overtone spectra, but also a collection of spectra that are second overtone. Looking around the room, who understands what that means? Steve does, Phil does, Uwe does. These peaks, the second overtone, are about 1/5 of the size of the first overtone. These are ripples that get smaller. Goes back to my question about the weighting yesterday. Why would you apply a linear weighting across the wavelength range when actually we know this collection is 5 times bigger than this collection is 5 times bigger than this collection? If you use a functional group from this collection and a functional group from this collection, you've already introduced a bias. You don't have a common response factor. You don't have a common response factor anyway, but you've got to understand where that comes from. I'm going to come back to that, but I do want people also to understand the importance of the measuring head. Measuring head focuses off in the distance. We're collecting diffuse reflectance spectra at a distance. If you change the angle of these collection fibers, you change the spot size. And there was a question yesterday about what spot size to use. This is real data, same spectrometer, different spot size. Larger spot, it looks like you've reached uniformity after 30 rotations. Exactly the same mixture, everything else the same. Smaller spot, I don't reach uniformity until 170 rotations. But fundamentally, this is observing a unit dose scale. So this is a genuine BU response. This is where you're looking at intra-dose distribution, clumping within doses. So it totally depends what you're looking at. And the key thing here is you need to choose a spot size to match. So the answer to the question of what spot size to use is, what are you looking for? You've got to answer that. Okay, I'm going to speed up a little bit because one of the fundamentals that we've got when we understand this is we can start asking the question of what about the near-infrared itself, the spectrometer itself. You know, most systems are still made from commercially available components, so that means we have to change what is commercially available. It's not simply that Uwe or anybody at Sentronic can build a spectrometer for whatever range you want. You have to actually provide the functional groups that are needed. But it's totally possible that these components can be optimized, and I want to talk about this just a little bit. So if we took the example that I've given up to now, a standard in-gas actually has a cutoff at 1700, but the energy has really died away at that point. You're in the noisy region, and we apply MAF treatments that are applied on a blockwise basis. It actually means the most important peak to us, the aromatic hydrocarbon peak, which sits at about 1660, I did write it on here, is so close to the cutoff of an in-gas that when you actually look at this in a spectra, I'm seeing the start of the peak. I don't see the peak. I know I don't see the peak because if I look at the second overtone peak, I can clearly see the peak. This would be a peak. We just do not see it in an in-gas. Anybody using an in-gas-based system, I'm talking about a standard in-gas-based system, if you've got an adequate concentration to be able to use this peak, absolutely fine. If you start being concentration limited, if you could use this peak, you would get 5 to 7 times greater sensitivity. I'm not telling you which spectrometer to pick, but understand if you are concentration limited, in-gas lets you look at this peak. There are solutions that let you look at this peak. Let's build on that concept just a little bit. And I said I was going to keep going back to this drawing. Well, these are repeating sets of information, the overtone peaks. This is a different set of information. You know, these are combination bands, these are overtone bands. You also have the overtones of the combination that really complicate you, but basically understand this is like repeating sets of data. So I'm going to do a little bit of audience participation. So question number 1, picture of a central pat BU. Who knows what the wavelength range is of the BU? Manel knows. Go on, tell us, Manel. Well, I won't challenge you. Yeah. Who knows why that is the wavelength range of the BU? Uwe does? When we're doing the blend operation, we can identify which functional groups we're looking at. We know the wavelength location of those functional groups, and this whole instrument is based on a spectral engine that was built to look at these functional groups. How many people actually think about that when they're choosing an instrument to select? I wouldn't say they don't. I wish they would, because it's not rocket science. It's really fundamentals. Just on this one example, I want people to understand what that means. Uwe mentioned yesterday that in the heart of the BU is this MEMS, miniature electromechanical spectrometer system from a company called Axon. There are actually 3 spectral engines that make up that unit. So actually, these 3 spectral engines are lights. They're basically tunable lasers that actually emit an output, but in very specific ways that they're actually overlapping. And it's the overlapping that gives us the range. Now I'm going to go back to my chart. If you remember, InGas missed here and was extended down to here. It's not that I don't care what's happening here. I don't need the information here if I have the first overtone information from there. This instrument, from the ground up, is designed, I'm getting carried away here, is designed to give us the wavelength range we need. If I was being honest, this engine wasn't designed for Sentronic. It was designed as a component that the industry could use. The first spectrometers in this range were not even from Sentronic. They're not commercially available anymore. The reason the Sentronic version is available is because they understood the impact of this measurement. Okay, this is very, very difficult to visualize, and you have to bear with me a little bit. This is a typical trend plot using a MEMS-based system. I see that there's a false end where it's reached gross blending very, very quickly, 25 rotations. But it's 200 rotations before I get to the point that there is no significant change in the trend. The grey box that's up here is the error bars that I would have if I did this same plot using an InGas-based system where I had to use the second overtone peak. So once I actually got into this grey box, I couldn't tell if I was changing or not. I was in the noise of the measurement system. By actually having the MEMS-based system, I can see that I'm still getting spectral change up to here. This is not always the case, but I'm trying to get everybody to understand that sitting underneath any of the data that we see are trends. Now, simply because it's 20 years ago, I'm going to do another confession. And it was a confession that at the time we had no idea of. Steve stood up in the science board meeting at the FDA and put up a trend plot that looked like it had two-phase mixing. We now know, looking back, the second phase of the mixing was simply the spectrometer was not stable. So you reached an end point, and then there was still spectral drift. At the time, we thought we were seeing an impact on the process. It's no one's fault. Think back to that earlier picture. We had a spectrometer that was duct taped to a computer that was bolted onto a spectrometer. We were starting to learn. But fundamentally, any of these trend plots have got observable variation underneath them. Okay, speeding up a little bit. Question 2. And now flipping to the FO. What's the wavelength range of the FO? A few more people know this. So it's a wider range. Why is it a wider range? Because we look at all of the components that we looked at with the BU, but this system is also used for granulation, where we can actually have a particular focus on residual moisture LOD. So what we're really doing is adding the OH regions to the BU spectrometer. It's a different heart in it, and it does actually beg the question, why is this instrument not an MEMS system? Why I said that these are spectral components that were built to enable the system suppliers to supply. If I look back to 2004, Axon were contracted to make not just a triple, but a quad system that actually included the OH regions. It also is a situation that this would have enabled the Sentropack dryer, which only had the OH regions. Don't worry about the stuff in between. The only reason there is no MEMS system is Axon never delivered it. If there are no fundamental components, these guys can't build spectrometers out of them. So the reason that, and I'll try to go backwards, the reason that this is an extended InGas and we've had to increase the range to add the water peaks, and just so everybody understands, particularly this higher region is very important because it can differentiate between free water, singly bound water, and doubly bound water. They're three different responses. We can not only say what is the residual moisture, we can actually say in what form that moisture occurs. This is absolutely fundamental in both granulation and drying of granulation. Confession time, this is one of Phil's photos from probably 20 years ago. I still use it because it's still valid. It lets people understand water has two arms. It's either not hanging on, but it's there. It's hanging on by one arm, or it's hanging on by two arms. We get a different spectral response. Everyone's looking at me as if I'm talking a strange language. Fundamentally, we've had a day and a half of presentations around using math to extract information. You can only extract information if you're collecting the correct information in the first place, and that's the core thing I'm trying to give here. Okay, question number 3. What's the spectral range of the DA? This is a little bit more tricky, and the Sentronics guys know this, because the spectral range of the DA is not to match the spectral range of the FO. What they've done is they've actually learned from one of the previous examples that I gave. I put this example up earlier on, where second overtone peak, can't do first overtone peak because it doesn't go far enough. Well, guess what? The DA has that extra spectral range, which means that you can actually see the whole of the first overtone. You can see the mag stearate peak. If anybody is comparing this to an InGas detector, I can guarantee you that because of the actual intensity of this first overtone peak compared to the first one, it's at least 20 times more sensitive. So fine buying an InGas-based system if you're not sensitivity limited. If you're sensitivity limited, and fundamentally, our API concentrations are getting lower, magnesium stearate is never in there at more than 0.5%. The only way you can see those is if you've got the extended range. Okay, I think I've labored a point. Hopefully, I'm trying to get people to understand when you buy a spectrometer, you understand what you're measuring and what range it covers. But there's an inverse of that, and I want to talk just a little bit about hyperspectral systems. Hyperspectral systems are not new. For years we've had spectrometers. They're not really spectrometers. They're integrated solutions that have got a whole range of technologies in them. Why are we getting some traction now? Well, why we're getting traction now is people are starting to understand that we're measuring different attributes, and you may well need a different measurement system for a different attribute. I said I was going to use one of Thomas's slides, and I finally get to it. So in this example, we actually have both near-infrared and Raman in the same probe. You could have had separate systems. It's important to understand, though, that this isn't simply we're acquiring two different types of data at the same time. You know, you can look and you can see the Raman data, the near-infrared data. The Raman data is very, very good at differentiating the active components. The near-infrared data is actually much better at discriminating the crystalline cellulose and mannitol. So you use the aspects of the spectra that it's better suited for, as long as the scrutiny of scale of what you're measuring is the same. There is a fundamental problem here. People have started using Raman for this application, assuming that if they acquire Raman over the same period of time, it gives them equivalent data. A 4 millimeter spot, 5 millimeter spot, you know, equivalent to the spot size of the near-infrared, penetrates by 5 millimeters. The sample mass in Raman is an order of magnitude larger. So if you acquire Raman data for a second, you actually, on a moving sample, you might be measuring a gram, 2 grams, where you're only measuring 25, 30 milligrams on the near-infrared. You've not got the same scrutiny of scale. But fundamentally, we need longer time with Raman. The signal's longer. So it's not uncommon to collect Raman data for 10 seconds, near-infrared data for 1 second. Guess what? You're looking at 20 grams versus 220 milligrams. How is that comparable? You've got to understand the difference. If Thomas was here, he could have drilled down into this a lot. I'm not intending to do that. I've got to finish off. But I do want to just finish off with getting people to understand that there's actually a whole new way of using PAT that's opened up. If we look at these spectral, multispectral systems in a development mode, where we actually look and decide what we need to measure, we can identify specific wavelengths that are linked to individual attributes. But then we can deploy sensors that are just looking at those wavelength regions. Now, I do want to finish just with a real example. And I said I was going to start by challenging you. I'm going to talk about absorbances in the mid-IR region. But I want people to understand that this is a fluorinated product. It's polyfluoropropane, a gas, which actually means the overtone peaks occur in the mid-IR region. This looks awfully lot like near-infrared spectra, because actually it is. It's overtone spectra that's just occurring in the mid-IR region. Forget the titles of UVVs, mid-IR, NIR. They're just describing wavelength range. Understand the attribute you're trying to measure. So, top example, lab bench, through a glass vial. So number one, I want everybody to understand, everyone says, oh, you can't do open bench mid-IR data. You can. This is measuring through a vial in headspace in transmission. It does work, providing you're not in an area where the light's all being absorbed. So this is bog standard FTIR, 4-second data. Let's use that line. The lower spectra looks very similar, but this is spectra acquired on a nonlinear IR in 20 milliseconds, because I know I only want this wavelength range. The instrument has been built to cover that wavelength range. So it means when my vials are coming off, 5 vials a second, I've got 100% inspection, 100%. I look at every vial and say whether it's good or bad. The rejection's based on that. But here's my closing thought before Sebastian hooks me off altogether.
It's in the interest of your troubles.
Yeah, it is. do I even need that whole spectral range when I actually know that there are 2 peaks, which we can well define, that by regression analysis give us a good regression. There's an area, a baseline, that also allows us to do baseline normalization. And just using a simple LED and a detector, I get perfect linearity across. There are a series of data points along that line. You can't even see them. So this, if I wanted to be crude about it, is a 3,000 euro measurement system. This is a 30,000 euro measurement system. This is a 100,000 euro measurement system. But fundamentally, if I do this on every vial, I can then look at the process dynamics to decide at what frequency I pull a sample and I still run the at-line measurement to confirm the online value. So the whole control strategy is around managing risk. Inspection, at a rate of inspection that's critical, we pull a sample. And my last comment on this, because everybody looks at this and says this must be development data. This is a commercial product on real-time release that was originally filed in 2009. This is a commercial product that we're running this on. This isn't an experiment or a demonstration. These guys are actually on their 3rd iteration of instrumentation for this process. It's classified as a packaging application because it's on the vial packaging line, so nobody would have heard of it. But outside pharma manufacturing, people have been doing PAT for many years. And with that, I don't know whether I have time for questions. I know I'm 2 or 3 minutes over, but thank you for listening to me.
As said, it's more in the interest of your travel schedule, and you have to catch the bus, you have to catch your flight, and so that was the reason I was showing up the 5. Thank you so much, Martin. Great talk, as usual, as expected, as predicted, as whatever. Questions to Martin?
I'm a little worried, Martin. I mean, this is a PAT conference, and you're trying to get us to do spectroscopy. I don't think that's going to work. No, really great talk. Do you see any challenges from the philosophy you're providing on more specialized sensors with regards to regulatory questions about expertise of the instruments? I think that's always been the pushback we've heard in pharma is, well, we could do LED solutions like we do in many other manufacturing environments. The concern is around life cycle management and around expertise of how these things work.
100%. And I would not be stood here giving this as an example unless I was also championing the use of the confirmation test outline. So understand what that means. And actually, I'm going to use the Bayer example from earlier on, where you looked at the trend in the process and it kicked up. You could quite happily be using LED-based measurements to monitor the flatness of the line, but you would need to actually pull a sample as soon as the process goes into what the regulatory description is a transition state. Startup is a transition state. Shutdown is a transition state. A process change as the process is running is a transition state. So I can't even stand here and say I only need to do 3 outline measurements per batch. If the process is perfectly stable, I need start, middle, end. Forget about it. If the process is all over the place, you need to actually be able to investigate and understand the cause of that, which is why the sensor is actually a low-risk impact. It's an inspection system. The outline confirms the observation.
So, thanks once more, Martin. Great to have you here, and great to pull you out.